Have you ever wondered why stars twinkle? That's our cosmic question for today. As we gaze up into the night sky, we're met with a celestial spectacle of stars that flicker and flash, creating a beautiful, twinkling canvas. It's a sight that has captivated humanity for millennia, sparking curiosity and inspiring countless tales and poems. But what's the real story behind this stellar phenomenon? The answer to this question, surprisingly, isn't found in the far reaches of space, but right here in our own backyard. Our atmosphere, the protective blanket that shields us from the harshness of space, is the key to this starry mystery. It's like a giant cosmic prism, bending and scattering the starlight in a myriad of different directions. So if you found yourself staring up at the night sky, captivated by the twinkling stars, you're not alone. Now, let's uncover the mystery behind the twinkling of stars. Stars twinkle because of a process called scintillation. Now that's a word you might not use in your everyday conversation, yet it's responsible for one of the most enchanting spectacles of the night sky, the twinkling of stars. So what exactly is scintillation? It's a term used in astronomy to describe the rapid changes in the apparent brightness and position of distant objects, such as stars. This is not because the stars themselves are pulsating or moving around, but because of the journey their light takes to reach us. Imagine the light from a star, millions of light years away, embarking on its journey towards Earth. This light travels through the emptiness of space, unimpeded, maintaining a steady brightness and direction. However, things change dramatically when this light reaches the boundary of Earth's atmosphere. Here, it encounters a turbulent, ever-changing medium full of air molecules. These molecules aren't evenly distributed, and their density changes with altitude, temperature, and weather conditions. As the starlight passes through these different layers of the atmosphere, it gets refracted or bent multiple times. Each refraction changes the direction and speed of the light slightly, causing the star to appear to twinkle and shift position. This constant bending and unbending of light, combined with our eye's perception of these rapid changes, gives us the twinkling or scintillation effect. It's like watching a coin at the bottom of a moving pool. The coin isn't actually moving, but the water's movement makes it appear so. So, the twinkling of a star is a cosmic game of telephone, where the message, in this case light, gets slightly distorted each time it's passed on. By the time it reaches us, the once steady beam of light has become a flickering, dancing spectacle in the night sky. But how does our atmosphere play a role in this? Let's find out. Our atmosphere, it turns out, is the real star of the show. So how does our atmosphere play such a significant role in the twinkling of stars? Well, the answer lies in the varying densities of the atmospheric layers. When light from a star passes through the atmosphere, it doesn't travel in a straight line. Instead, it bends and refracts or changes direction and speed. This is due to the different densities of the air at various altitudes. Each layer, with its unique density, bends the light in a different way, causing the starlight to take a zigzag path to our eyes. Now consider this. Our atmosphere is not a static entity. It's constantly in motion, with air currents swirling and mixing, heat rising and falling, creating what we know as turbulence. This turbulence amplifies the bending and refracting of light. When you look up at a star, you're not seeing one steady stream of light. You're seeing multiple streams, each refracted differently by the atmosphere, reaching your eyes at slightly different times. This rapid, random shifting of light paths is what causes stars to twinkle. Imagine standing by a pond and throwing a stone into it. The ripples that spread out aren't uniform, are they? They interact, interfere with each other, create patterns. That's precisely what's happening with the starlight in our atmosphere. The light waves are like ripples, and the turbulence in the atmosphere is like a multitude of stones disturbing the water simultaneously. It's a dance of light and air, a cosmic ballet. The twinkling stars are the performers, but the atmosphere is the stage, the director, the choreographer. It's a spectacle of nature that we've admired since the dawn of time, and yet it's all down to the physics of light and the nature of our planet's protective shell. But here's the catch. This effect, while beautiful, does have some implications for astronomers. Opening, while twinkling stars are a delight for stargazers, they pose a bit of a problem for astronomers. The beauty of a star-studded night sky is undeniably captivating. Each twinkle, however, is a testament to the unpredictable dance of light as it journeys through Earth's atmosphere. For those of us simply enjoying the view, this shimmering spectacle adds to the charm. But for astronomers, it's a different story. You see, astronomers are like detectives of the universe, constantly seeking clear, unobstructed views of celestial bodies. Twinkling, or to use the scientific term atmospheric distortion, can often be their nemesis. It's akin to trying to discern the details of a pebble sitting at the bottom of a rippling pond. The distortion caused by the water's surface makes the task quite challenging. In the same vein, the Earth's atmosphere acts as a turbulent, distorting lens that blurs the crispness of celestial images. When light from a distant star enters our atmosphere, it doesn't follow a straight path. It bends, refracts, and dances around, distorted by temperature differences and turbulence in the air. This results in a star that appears to twinkle and shift position, making it difficult for astronomers to capture accurate and reliable data. In addition, the atmospheric distortion also impacts the brightness of celestial objects. The constant change in the atmosphere can cause a star to dim and brighten rapidly, affecting the precision of photometric measurements. These measurements are crucial for many astronomical studies, such as determining the size and distance of celestial bodies, or tracking changes in a star's brightness over time. Moreover, atmospheric distortion can even impact our perception of a star's color. As the atmosphere bends different colors of light by varying amounts, it can cause a star to appear to change color momentarily. This chromatic aberration can add another layer of complexity to astronomical observations. Closing, so how do astronomers deal with this twinkling issue? Astronomers have developed a technology called adaptive optics to combat the twinkling problem. Imagine you're looking at a pebble at the bottom of a stream. The flowing water distorts the image of the pebble, making it seem to dance and shimmer. This is similar to the challenge faced by astronomers when they observe stars through our turbulent atmosphere. This is where adaptive optics swoop in like a superhero. It's a sophisticated technology that measures atmospheric distortions in real time and adjusts accordingly to produce clearer images. Let's break that down a bit. Our atmosphere is like a fast-flowing river of air, constantly shifting and changing. This turbulent air causes the starlight reaching our telescopes to distort and flicker, much like the pebble in the stream. Adaptive optics works by using a special device called a wavefront sensor to measure these distortions. The wavefront sensor takes rapid-fire readings of an incoming starlight's wavefront, which is essentially a surface over which light has a constant phase. As the starlight passes through our atmosphere, the wavefront gets distorted, much like the ripples in our stream. These readings are then fed into a computer, which calculates how to adjust the telescope's mirror to compensate for the distortions. The mirror, made up of hundreds of tiny, flexible segments, can change shape in real time to counteract the atmospheric effects. This results in images of celestial bodies that are as sharp and detailed as if they were taken from space. It's like having a pair of glasses that can constantly adjust to give you the clearest vision possible, no matter what's happening with the atmosphere. This technology has revolutionized ground-based astronomy, allowing us to see distant galaxies, nebulae, and even planets orbiting other stars with unprecedented clarity. With adaptive optics, astronomers can see the universe more clearly than ever before. Through the looking glass of adaptive optics, we're able to gaze deeper into the cosmos, peering into the very heart of the universe itself. The twinkling of stars, once a hindrance, is now helping to shape the future of astronomy. Our understanding of this phenomenon and the development of technologies to overcome it are leading to advancements in astronomical observations and discoveries. Let's consider the advancements in adaptive optics, for instance. These systems have allowed us to correct the distortions caused by atmospheric turbulence in real time. This has led to much sharper and detailed observations than ever before. Telescopes equipped with adaptive optics, such as the Keck Observatory in Hawaii, are already providing astronomers with unprecedented views of the universe. The future holds even more promise. The upcoming generation of extremely large telescopes, like the 30-meter telescope and the European Extremely Large Telescope, will feature even more advanced adaptive optics systems. These behemoths will be able to collect more light than ever before, allowing us to peer deeper into the cosmos and uncover its mysteries. And it's not just about better images. The ability to reduce atmospheric distortion also opens up new possibilities for spectroscopy, the study of the interaction between matter and electromagnetic radiation. This will allow us to analyze the chemical composition, temperature, and velocity of celestial bodies with greater precision. Furthermore, the advancements in understanding the twinkling effect have also played a crucial role in the development of interferometry. This technique combines the light from 2 or more telescopes to create a single, high-resolution image. It's like having a telescope as big as the distance between the 2 telescopes. This has the potential to revolutionize our understanding of stars, galaxies, and other celestial objects. In essence, the twinkling of stars, which once posed a significant challenge to astronomers, is now a well-understood phenomenon. And the technologies developed to overcome this challenge are paving the way for a new era in astronomy, an era of unprecedented clarity and discovery. So the next time you look up at the twinkling stars, remember there's a lot more going on than meets the eye. We've traveled quite a distance today, from our own atmosphere to the far reaches of space. It's been an illuminating journey, one that's taken us from the comfort of our own backyard to the frontiers of scientific discovery. We've delved into the science behind the twinkling of stars, a phenomenon that's not only beautiful, but also incredibly complex. We've discovered that this twinkling, or scintillation as it's scientifically known, is caused by the Earth's atmosphere. The layers of air, with their varying densities and temperatures, bend and distort the light from stars. This refraction results in the star's light reaching us not in a steady, constant stream, but in a fluctuating, twinkling pattern. But we haven't stopped there. We've also explored how this atmospheric effect, while beautiful to the naked eye, poses significant challenges for astronomers. The same twinkling that captivates us also blurs and distorts the images captured by ground-based telescopes. It's like trying to discern the details of a painting while looking through a rippling pool of water. Yet, as we've seen, these challenges have not deterred the human spirit of exploration and discovery. Instead, they've spurred the development of innovative technologies like adaptive optics. These systems, which adjust and correct for atmospheric distortions in real time, are helping astronomers to see the universe with unprecedented clarity. The journey we've embarked on today is a testament to the power of human curiosity. It's driven us to understand why stars twinkle, to probe the complexities of our own atmosphere, and to devise ingenious solutions to see past these complexities into the heart of the cosmos. And while we've reached the end of this particular journey, the exploration is far from over. The universe is vast, and there's so much more to discover. So as we conclude, remember this: the twinkling stars are not just a beautiful spectacle. They are a reminder of the challenges we've overcome, the knowledge we've gained, and the mysteries that still await us. Thank you for joining us on this journey through the cosmos. Stay curious and keep looking up. Before we draw the curtains on this cosmic journey, we'd like to leave you with a few parting words. If you've learned something new from this video, then we've accomplished our mission. Our goal is to ignite curiosity, inspire learning, and make the vast universe a little more accessible to everyone. If you've enjoyed this exploration of the twinkling stars, then please give a like to the video. It's the best way to let us know that we're on the right track. But it's not just about us. We want to hear from you too. Share your thoughts, questions, and insights in the comments section. Did this video change the way you look at the night sky? Did it spark a new interest in astronomy? Or perhaps it inspired you to learn more about the science behind everyday phenomena? Whatever your thoughts, we're eager to hear them. And lastly, don't forget to subscribe for more such content. Our journey through the cosmos is far from over, and we'd love for you to join us on future expeditions. Also, consider sharing this video with your friends and family. After all, the joy of discovery is all the more sweeter when it's shared. Thank you for joining us, and remember, never stop looking up.